In the paper, Heteroskedastic Geospatial Tracking with Distributed Camera Networks, the authors present a novel approach to geospatial object tracking using a distributed camera network. This task involves detecting and localizing objects as they move through a scene, with the goal of predicting an object's track in geospatial coordinates along with uncertainty over the location. The author's work is motivated by the proliferation of IoT devices with local sensing, compute, and wireless communication capabilities, which have important applications in smart cities such as traffic monitoring and pedestrian safety. The paper begins by discussing related work on tracking, including model architectures, multiview computer vision, and probabilistic tracking. It highlights the limitations of traditional tracking benchmarks that assume access to high-quality video data and focus on the multiview geospatial tracking problem. The authors then introduce their custom dataset, which includes high-accuracy ground truth object locations collected at 100 samples per second using a motion capture system, combined with video from 4 camera nodes with different partially overlapping views of the environment. This dataset spans multiple scenarios, including an open environment and an environment with occluding structures, as well as normal and low lighting scenarios. The authors present a modeling framework for addressing this task, which involves augmenting neural network object detection backbones with adapters that translate within image features into geospatial coordinates with associated uncertainty. They explore how uncertainty calibration and fine-tuning through a differentiable tracker affect performance. The authors experiment with both existing and custom backbones within the HGDs and assess the impact of geospatial detection calibration and fine-tuning on tracking performance. The paper concludes with a discussion of results, showing that recalibrating the output of the HGD models using an affine transformation of their raw covariance outputs can significantly improve the log likelihood of true object locations. Fine-tuning by backpropagating through the Kalman filter further improves performance for most HGD models. The authors also demonstrate that their custom HGD backbone can provide performance on par with ResNet 50 and Dieter backbones under normal lighting conditions while simultaneously providing significant improvements in runtime latency. Interestingly, they show that in the low-light condition, the DETRBASED model has remarkably more robust performance than the other models considered. The research paper discusses the development of a heteroskedastic geospatial tracking model framework for object tracking in various scenarios. The framework consists of heteroskedastic geospatial detection (HGD) models and a geospatial tracker (GST) based on a multi-observation Kalman filter. The HGD models predict a full covariance normal distribution over the location of the object in geospatial coordinates, while the GST component filters these predictions to generate smoother trajectories. The framework is tested using 3 backbone models: ResNet 50, Dieter, and a custom model. The custom model is found to be the fastest, with a runtime analysis showing it to be 6 times faster than Dieter and 2.5 times faster than ResNet 50. The paper also includes details on data collection, including scenarios with open and occluded environments, and data preprocessing techniques. Here is a combined summary of pages 5 and 6 of the research paper. The authors propose a heteroskedastic geospatial object tracking (HGD) model that predicts the mean and covariance matrix of a Gaussian distribution representing the location of an object. The HGD output head takes a 256-dimensional encoding and outputs 5 values, with the first 2 values determining the mean location and the remaining 3 values predicting the covariance matrix. The authors also utilize a constant velocity multi-observation Kalman filter-based tracker (GST) to fuse detections from multiple views. The GST model is a dynamic Bayesian network with Gaussian distributed latent state, representing the location and velocity of the object being tracked. The authors evaluate the performance of their HGD model using various metrics, including negative log likelihood (NLL), object probability mass (OPM), detection recall and precision (DET-PR), and location accuracy (LOCA). The NLL metric evaluates the quality of the model's output using the negative log likelihood of the Kalman tracker's marginal distribution over the object's location. The OPM metric computes the predicted probability mass that falls within the ground truth extent of an object. The authors present baseline performance results for both normal light and low light data scenarios, using 3 backbone models: ResNet 50, DETR, and their custom model. The results show that the DETR backbone achieves better NLL in the low light setting and outperforms the other backbones in terms of OPM and tracking metrics. The authors also experiment with the effect of Kalman filtering, comparing the average performance of 4 HGD models to the performance of the baseline Kalman filter model. The authors use a range of techniques, including sigmoid activation, soft plus function, and matrix multiplication to ensure numerical stability and positive definiteness of the covariance matrix. They also employ Atom W optimizer with weight decay and gradient clipping to train their models. The author's approach enables efficient and accurate object tracking in geospatial environments, with potential applications in various fields such as surveillance, robotics, and autonomous systems. In this research, we focus on the geospatial object tracking problem using data from a distributed camera network. Our goal is to predict an object's track in geospatial coordinates along with uncertainty over the object's location. We have presented a novel single-object geospatial tracking dataset to support this work that includes high-accuracy ground truth object locations and video data from a network of 4 cameras captured under normal and low light conditions. We have presented a modeling framework for addressing this task that leverages a multi-observation Kalman filter-based tracker in conjunction with a set of independent heteroskedastic geospatial detection models. This framework is specifically motivated by a communication-constrained version of the tracking problem where it is too expensive to centralize raw image data and thus late fusion of low-dimensional representations is required. Our results show that using the tracker leads to much better performance on the OPM metric. This suggests that the individual HGD models are producing higher uncertainty and larger covariance than the Kalman tracker output. This results in a higher OPM score as the OPM metric is highly sensitive to the scaling of the covariance matrix. However, we see that the average NLL across the 4 HGD models per backbone is actually better than the NLL provided by the Kalman tracker in all but one case. This suggests that from a predictive likelihood standpoint, the baseline Kalman tracker is actually underrepresenting uncertainty. We address this issue in the next experiments. Experiment 3: Post hoc model recalibration. Inference in the Kalman tracker is fully differentiable. It is thus possible to learn while backpropagating the Kalman filter's NLL through both the parameters of the Kalman filter and the parameters of individual HGD models. We refer to this approach as Kalman filter fine-tuning. In our implementation of the constant velocity Kalman tracker, the standard deviation of acceleration parameter is the only learnable parameter. However, this parameter is important as it determines how much the Kalman filter's uncertainty over its internal latent variables increases between observations, which has implications both for the uncertainty in the tracker's output and the degree of smoothness in the output track. Further, Kalman filter fine-tuning allows the output heads and adapters inside the HGD models to adjust themselves to the tracking scenario. For computational complexity reasons, we do not consider full end-to-end training of the backbones. We present results for this setting in Table 6. The results reported are using calibrated HGD models as described in the previous section. The reported NLLs are computed with respect to the Kalman tracker's output distribution. We see that applying Kalman filter fine-tuning results in an improvement in our custom model on both data scenarios. Surprisingly, the DETR baseline sees worse NLL performance on both data settings. After calibrating and training through the Kalman filter, our custom model is able to achieve better NLL score than DETR in the normal light scenario at 6 times lower latency. It is also able to close to within 0.5 nats of the performance achieved by the ResNet 50 backbone in the normal light scenario at 2.5 times lower latency. Lastly, despite the fact that the DETR-BASED model does not improve in performance under Kalman filter fine-tuning, it remains the best performing model in the low-light scenario by a wide margin. The paper provides a comprehensive overview of the field of multi-object tracking, focusing on the application of transformer models to this task. It begins by discussing the challenges and limitations of traditional computer vision techniques for visual tracking, highlighting the need for novel approaches that can effectively handle complex scenarios involving multiple objects. The authors then introduce the concept of transformer models, which have shown promising results in various domains such as natural language processing and image recognition. They explain how these models can be adapted for multi-object tracking tasks, leveraging their ability to capture long-range dependencies and contextual information. The paper also reviews several state-of-the-art transformer-based methods for multi-object tracking, including TrackFormer, Motor, and DETR3D. These approaches utilize different strategies to integrate transformer layers into their architectures, such as using them as feature extractors or incorporating them into the loss function. In addition to discussing the technical details of these methods, the authors also address the challenges associated with applying transformer models to real-world scenarios, including issues related to computational efficiency, data requirements, and model interpretability. The paper concludes by emphasizing the potential benefits of integrating transformer models into multi-object tracking systems, particularly in terms of improving accuracy and robustness in complex environments. However, it also acknowledges the need for further research to overcome the aforementioned challenges and ensure widespread adoption of these techniques. Overall, the paper presents a thorough analysis of the current state of transformer-based multi-object tracking, highlighting both the opportunities and challenges in this rapidly evolving field.